Standard vision language models fail when deployed into physical environments that spontaneously shift and evolve during execution. They cannot adapt their pre-trained assumptions to match immediate, real-world chaos. To manage complex reasoning, engineers typically rely on a mixture of experts, or MOE, architecture. This structure compartmentalizes different types of knowledge, allowing a system to select specific expert models for specific tasks. The structural flaw with conventional MOE is that its routing mechanisms operate entirely over latent representations. The system lacks any explicit, measurable metric for scale, meaning it cannot distinguish between high-level abstract logic and low-level physical dynamics. This diagram illustrates the mixture challenge. Without a scale access, error updates blast uniformly into every world model. This creates the evolution challenge. A tree's physical state changes rapidly, requiring fast adjustments, while a forest remains stable. A single uniform policy cannot accommodate both. Applying a scale-blind MOE system to a physical robot forces an impossible compromise. The agent will either suffer catastrophic forgetting of its high-level logic, or it will face a fatal lag in updating its low-level physical reactions. Routing mechanisms for embodied agents must be explicitly grounded in a measurable, continuous scale axis. The MuSix framework is built on this exact requirement. It is an architecture designed to dynamically mix and evolve world models across different scales of reasoning, isolating physical reactions from abstract planning. The mechanism driving this architecture relies on a metric called experiential distance, adapted directly from Construal Level Theory in psychology. Construal Level Theory dictates that psychological distance determines abstraction. Experiential distance applies this to machines by measuring exactly how novel a current situation is relative to the agent's accumulated memories. Explicitly calculating situational novelty provides the mathematical foundation required for targeted adaptation. It gives the AI a numerical trigger for when to rely on concrete physics and when to zoom out to abstract strategy. To function in real time, the system must continuously measure how highly unusual a current scenario is compared to past operations. The agent tracks its accumulated experience as a sequence of recent observation embeddings. This sequence of embeddings is modeled mathematically as a multivariate Gaussian distribution. Older memories fade, prioritizing the robot's most recent physical context. When a new observation occurs, the system calculates its Mahalanobis distance against that established cluster, the core metric. A highly familiar situation yields a low scalar value. The system recognizes the routine environment and triggers concrete, low-scale execution models to handle standard physical tasks. A highly novel situation yields a large scalar value. Recognizing the unfamiliarity, the system triggers abstract, high-scale reasoning models to generalize and plan a way out. This continuous scalar translates the vague psychological concept of novelty into a precise mathematical trigger, instructing the architecture exactly which cognitive level to deploy. To utilize that trigger, MuSix dismantles the flat MOE router and decomposes the selection process into two distinct stages. This diagram details the Stage 1 routing process. The continuous meta-router maps the experiential distance scalar directly to a specific weight function over a continuous scale space. When experiential distance is low, the meta-router concentrates its mass exclusively on low-scale physical dynamic models. When experiential distance spikes, the meta-router shifts its weight upward to high-scale cognitive maps. In Stage 2, once the correct scale is identified, per-scale base routers select the specific top K world models within that group to execute the task. Decoupling the scale determination from the expert selection solves the mixture challenge. The system finally has a transparent, isolated target for test time updates. That isolated target enables the knowledge adaptation module, which is explicitly designed to solve the evolution challenge. Here we see intrascale adaptation. The meta-router isolates the active scale, distributing knowledge increments strictly to the relevant group. The framework then applies differential forgetting rates. Low-level sensory groups get rapid forgetting rates, instantly dumping outdated physical data when environments shift. High-level expert groups utilize slow forgetting rates. This protects their data, retaining abstract reasoning rules and broad strategies over extended periods. To prevent these groups from turning into isolated knowledge silos, Interscale adaptation relies on gated bidirectional matrices. This allows critical information to transfer between adjacent scale groups, maintaining coherence across the hierarchy. This dual adaptation mechanism allows a robot to instantly relearn the physical friction of a newly slippery floor, without forgetting its high-level objective to leave the room. We can observe this architecture performing in the hazard simulation benchmark, designed to evaluate agents in environments that spontaneously evolve over time. In the flood scenario, rising water introduces new buoyancy and drag forces. These fluid dynamics actively invalidate the agent's initial physical assumptions about objects in the room. Standard scale-blind baselines like Sake and Pay and Flare suffer high damage ratios in this test. Their uniform update policies cannot adapt their low-level reactions to the water fast enough. MuSix significantly reduces the damage ratio, dropping it down to 4.65. The agent rapidly isolates and updates its low-scale physics models regarding the water flow while perfectly maintaining its high-level rescue strategy. Scale-aware adaptation translates directly to physical survival in unpredictable environments. When we examine the ablation study data from the Embodied bench trials, we see a severe drop in performance the moment the meta-router is removed from the system. Removing the meta-router forces the architecture back into scale-agnostic routing. The framework's efficacy collapses, pulling the success rate from 40.4% down to 32.2%. Monolithic test time updates are incompatible with the chaotic reality of physical robotics. Modular systems that can evaluate, target, and evolve at different cognitive frequencies simultaneously are a strict requirement for embodied AI. By translating the psychological concept of novelty into a continuous mathematical scale space, MuSix provides a viable blueprint for real-time machine adaptation.